Okay, today for the lecture, we are going to talk about some side topics. They are not, there is no calculations, more informative topics. And then we will talk about weir and so on, which is very important as well with respect to the journal bearings. The first thing that we think part that we want to talk about is the bearing types. And if you see in this figure here, we have um, what what appears to be four types: A, B, C, and D, or basically they are four, two under the category of a sleeve bushing. And if you think about it, we have a solid bushing, so one complete sleeve, hollow thin cylinder, and the other one is called the line bushing. So as for category A here, these are examples. I think the most famous one of all is the sleeve which Starbucks uses in their coffees. So if you go get a hot drink from Starbucks, not the one which is mixed usually with milk and other things, they will sleeve the cup for you, and that little strip, okay, of made of from hard brown papers, um, will be sleeving the cup so you hold it and you didn't get burned. The interesting part, if you have tried this, if you haven't tried it, go one day and unfold that sleeve. And on the side, I think maybe you don't need to fold it, but if you have to, search for the patent number just to make it fun a little bit. That sleeve is patented, and honestly, I ask the student in the other section, so maybe I ask you as well. One day, within the next period, if you get the chance to go to Starbucks and you get that sleeve, go and search the patent number. Let's see who can tell us that patent is registered under whom. Because for me, I think it is registered under Starbucks. Nobody is using sleeves in the entire planet, so probably Starbucks um, uh, made the patent. It is now reserved for them. Nobody can use it. If it is some other company, then probably that company will license the patent to Starbucks, will license it to others. But maybe I don't know. That's an interesting sleeve. Okay, so that's one type sleeve. طبعا يا شباب, um, I spoke about that sleeve here, but maybe I should speak about it on the next slide, which is when we talk about the lined bushing, where we have this cut over here. Starbucks sleeve has a cut, then it can, kind of clamps to hold itself. So in this type, basically, I have added here some text explaining to you how these bushing are made. So by molten material and then making it a thin, strip, and then they batted it and so on. Of course, such cut, which is like a groove, is probably intentionally made to facilitate oil. So this is like a grooved opening. Okay, and the the most famous of all, I would say, is this guy. I think if you go to any machine shop around, the closest one is the Aramco Dahran machine shop, if you happen to be there, which is the straight, like two pieces. This is the other category, is two pieces bushing. And uh, I think, Yashabab, this is not a good example. I searched for a flanged bearing, and I think probably this is the flanged bearing, and this is a straight bearing, and this is not actually a straight. So, but in the end of the day, this is a two pieces. If you go to that machine shop, you will see that when they receive the equipment, they will dismantle the casing, the top part of it, and then the bearing will be exposed. There are some screws on the side. They will unlock the screws, and then they will take half of the bearing from both sides. Then they will hook the the rotor. The rotor is basically the shaft with everything on top of it, blades, impellers, you name it. And then they will pick up the lower part and then go clean them, maybe replace them, do whatever you want. If you zoom in here, you will interestingly see the pads, right? So these are the guys that are basically carrying everything. Yeah, this is where the thin film, the lubrication, Reynolds equation, temperature, everything we did, all the mathematics and design is happening. Okay, interesting. Now, uh, let's move on. This kind, I'm not gonna lie to you, this kind of type, this kind of bearing, I mean, this type of bearing, where you see the journal or the bearing has some some grooves to facilitate the distribution of the lubricant. I honestly haven't seen it before, but it is there for you to see. So this is, if you zoom in here, you see that there are very thin grooves. These grooves basically facilitate the distribution of the lubricant all over. Okay. Now, now what are we gonna talk about? Is this? Um, have you ever thought about something which is when we studied bearings, like the roller contact bearings, we spoke about thrust. And actually, it turns out that thrust is this um, unavoidable force, uh, which you can deal with. You remember, we had uh, the arrangement to put two helical gear against each other in a way to cancel out the thrust, and we said in other situation, um, we can have um, uh, thrust bearing. So we talked about the groove bearings handling thrust. We talked about uh, roller tabled bearing handling also the thrust. But with journal, this little nice cylinder, you can imagine that you can just float in the axial direction. So what is going to stop you? What? So one way is to have, with the same logic, a thrust bearing. So I would rather have this diagram, this figure, blotted in this way. So basically, you can imagine that you have a pad. This is the pad. This is just like ya shabab brakes. Okay, these grooves are there to facilitate lubrication, and then you have a runner. This guy is the one that rotates. But in the end of the day, the principle is very simple. You have a surface and another one. The other one is rotating because it is attached to the shaft, possibly. And what you want to make sure is that the force pushing against will be resisted by the pads. And now what you need to worry about is this friction generated while these are being pushed against each other. Well, this is very interesting. So you can just, if you ensure that there is lubrication, then you are gonna be basically having a thrust bearing. But you need to be very careful. Now I know this may sound a little boring, but I'm gonna read this note for you. Okay, so just be watch out with me. It says we should note that bearings are frequently made with a flange as shown. So what a flange? It means that you have here this side. I'm trying to highlight it with the green. Green is very light color, so maybe I put a red over here. See that part? This is like there is a flange, and then there is the shaft is pushing against it. Now the flange position, uh, the bearing in the housing, and also take care of the thrust load. Even when it is grooved, however, and has adequate lubrication, such arrangement is not theoretically a hydrodynamically replicated thrust bearing. So, if you remember, back in the first class of this chapter, we talked about the category, right? And we said we have a hydrodynamically lubricated bearings, we have boundary lubricated bearings, and we said that these two categories are different. Now, the reason for this is that the clearance space is not wedged shaped, but has a uniform thickness. So, if you just recall, what we did with with the cylindrical shape, okay? Well, started with the famous work of Reynold when he said, "Oh, this is the journal, and this is the bushing." Okay, this is exaggerated, and what he did is that he assumed that this area is like this. Do you remember? And what does that mean? It means that he said, okay, I'm going to assume that the the surface down of the bushing is straight, and I will assume that due to the eccentricity. Of course, here he's saying that it's not that the journal is not big enough to assume that the curvature is almost a straight line. No, he's assuming that this wedging is happening because of the eccentricity that we talked about. And by doing so, I mean, not we, the, you know, Reynold. So, His Majesty. So, what he did, he said, okay, if you recall, we said that the flow will go from one side to the other, and we took an element, we explained that there is shear stresses, we explained that uh, the the pressure is constant along this line and changing that line and so on. Okay, and and um, and that's how the whole mechanics was derived. The S number and everything followed up from Reynolds equation. But in here, what we have is a true, most likely, a boundary lubricated bearing. And just to remind you about the boundary lubricated bearings, we showed you, if you go again to few slide later, this is very exaggerated view of the surfaces of, let's say, the bad and the bearing. Now, and or the journal and the bushing. So what we said there is a layer, a boundary layer of the lubricant sticking here. This layer is always there, and in between we have a lubrication. This is what we have, a hydrodynamically lubricated system. And this is a flowing, and there is a wedge, and there is a pressure difference, and so on. But also, if you go back, we told you that with boundary, okay, we have something like this, okay, and the line here, you see, where the boundary lubrication exists is very thin, and there are a few gaps where I can try to fill them with little oil over here, very little. So metal to metal contact become concern. Yes, and it says here, when two surfaces slide relative to each other with only a partial lubricated film between them, boundary lubrication is said to exist. And then when we have and sometimes, you remember we said sometimes boundary lubrication, which is a very thin film lubrication, even occur in hydrodynamically lubricated system. When? When there is a starting, stopping. Do you remember? We said the starting of the turbine, the beginning of it, and the stopping, when the load increases, when the supply of the lubricant decrease, and so on. Even when the characteristics, temperature, and so on, viscosity changes. Now, so this becomes of a concern. The you know there is a come on. I mean, you look at this, you would say, I probably will never avoid some touches between the two metals. Now, so what people did, they said, first of all, after some studies, they understood that animal, interestingly, animal and vegetable oils are actually helping. They have what is known as fatty acids. These fatty acids stick to the metal, fill those little asperities and gaps, and then helps out reducing the friction. But you should be careful that these little fatty acids kind of dissolve or disintegrate whenever you reach a temperature of about 250 degrees Fahrenheit. And that's just, not a coincidence, right? That number, we know it from Timbeler recommendation. So it makes now a whole lot of story. So what you can do, you can basically minimize the metal to metal by mixing the oil, the lubricant, with animal or vegetable oil. You can use porous metallic material, non-metallic material, and so on. So here what we have some materials for boundary lubricated bearings, like some of them like cast bronze, porous iron, and so on. Some of them even non-metallic, like nylon and Teflon, and so on. What we have here, a maximum load capacity, temperature, speed, and then the product BV, which we will make sense in a bit when we talk about wear in advance. This slide should come after the next one, so I'm gonna rearrange this and then post it in the blackboard. So what are we interested in now is this. Yes, we spoke about thrust bearing, and we said that it is mostly, flat and but in reality, as per the material, we are not going to have a problem or design problems which need a thrust, where this is, two disc close to each other. This is not something that we are going to discuss. Okay. But the concept of the wear is very important. Why? We just said that hydrodynamically lubricated system, which has a thick film, can encounter boundary in starting, stopping, increasing the load, and so on. And this means that there is wear. There is a metal to metal contact. So the purpose of the coming few, you know, sections, I think two or so, is to study wear. Now, wear is the removal of material by some process through friction. So if we would want to establish some basic foundation to study wear in the material, we came to a very simple example. Now, I found myself, facing hard time recognizing this figure. Somehow, I think they should have made it this way, but I assume that they wanted to show us the surface underneath, and that's why they plotted this way. So let me explain to you. This is the bottom surface. This is the front, and this is the side. So what you imagine here is this. You imagine in a simple way, small rectangle, no big deal. That's what how do we usually do it? When we apply a force over this block, okay, and there is a surface underneath it, of course, then we know that there will be an opposite force, which is equal to the pressure generated multiplied by the area, the projected area. That's just a reaction. Now, if you happen to push this block while the force is in there, then due to the friction, that force is going to be equal to Fs, the sliding friction, multiplied by the pressure multiplied by the area. And you will be encounter opposed by a shear stress tau A, correct? Now, if you slide this block at a distance S, some material will be removed, and that removed material is, in terms of thickness, is being designated as W. Okay? Now the question is, it doesn't matter. You want to know this removal rate, which is expressed as the wear rate, or you want to know how much wear, how much you are losing. So if we just imagine that I want to know how much I am losing per unit time, which is hour or whatever, then it is W divided by T. It's a rate. That's why there is a time here. And then we have two coefficient of frictions, actually two coefficient. They are called modifying factor. It's not the coefficient of friction, I'm sorry. The first one, F1, depends on the motion type, load, and speed and environment, while F2 accounts for temperature and cleanliness. How clean is this and what is the temperature? Okay. K, if you look at the unit of K here over there, it is inches cube, so that's unit of volume multiplied by time, divided by a force, bound force, distance, feet, hours. You would imagine that this is a measure of some sort of how much is being removed. And you can imagine that if you have cheese, steel, wood, a block of cheese, a block of steel, a block, and you run them over a rough surface, you would imagine that, how much of the material that is removed is different. So this is actually a characteristic, and it is a wear factor that can be found for specific material. It's a wear factor. It's the material ability to resist. Okay? And then we have P, which is the pressure, by V. These two seems to be very relevant. I mean, come on, if you put the block and lightly and then you start moving it, you will feel different. If you put it lightly and you move it fast, you will feel different. You will get different result. If you push it too hard and slowly, you will get something different. And if you push it hard and you slide it too fast, you will also get something different. So these two has to be there. So the P is the pressure in PSI. The V is the velocity or the speed per, feet per minute. T is the time per hour. And we just explained K, which is in centimeter, usually described in centimeter cube minute per kilogram force. Kilogram force, 1 kilogram force is equivalent of basically 1 Newton. Not 1 Newton, 9.8606 Newton. Meter hours, that's the unit. Now, if we go back, I told you, so if you go back here, you will see some materials used for bushing. So this is the bushing material. This is oilies 800, oilies 500, nylon, polycarbonate, and what is their wear factor? This is in US customary unit, okay? And this is the limiting BV, which is there is a limit by which you can combine this pressure and velocity. And of course, thus the coefficient of friction Fs is given here for different materials as well. Okay? Now, what are the, let me just zoom this out. What are F1 and F2. F1, which is the motion related factor, since it is motion related factor, you should expect that there are some categories. So we have here a rotary motion, we have an oscillatory motion, and then we have a reciprocating motion. Yeah. And we have a pressure, so we need to know what pressure, and of course, what is the range of velocity, and F1. F1, for most part, is not one number, so it is more of a range, okay? And then we have the environmental factor, F2, which is given for what temperature below or above, and if there are foreign matters. So if you're expecting dust to go in and so on, you need to take that into account as a foreign matter. Why? Because we said that this is dependent on the cleanliness and the temperature. So the cleanliness is more of related to what are the possibilities of having a foreign material getting into the system. So if we want now to establish a neat relation for what is supposed to be a weir, want to now study weir. Why? Because it is unavoidable, period. So don't be a coward and say, oh, no, 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 it's not going to happen. And you just deny it. It is there. So you better deal with it. So we will here consider a pen. Okay? Now, so just to tell you, why do we consider a pen? We are establishing the weir relation for a cylindrical geometry, not like the a flat, two disc against each other. This is just to tell you. Now, so we will have a pen. Oh, not this one. This is a pen with a diameter D and length L. So this length is L. And of course, this pen is rotating with a speed N. You see that? And it has been subjected to what? To a force F. Now imagine that this guy is rotating, okay, in a bushing. So, like, I mean, a bushing, we are assuming that this pin is sitting on a half wedged cylinder, right? And then what is the pressure? Well, starting easy, we don't know what is the pressure, the distribution of the pressure. We don't know it. So starting easy, we will say we will take the nominal pressure. What is the nominal pressure? It's the projected pressure, or the pressure generated from the projected area. How is that calculated? Well, you will assume that you have a projected area which has a diameter d of width and a length L, and then that force over here is going to generate this stress in here, which is equal to P equals to that F divided by the area, which is equals to F dl. Is that okay? That's the nominal. Nominal. Now, if we assume that the velocity is measured in feet per minute, and the diameter is measured in inches, and n is measured in revolution per minute, then the velocity is going to be by dn divided by 12. Remember, whenever you have something in feet and something in inches, that 12 will come because you need to convert, right? 1 foot has 12 inches. Okay? So if we know the velocity, though, and we know the pressure. So the term BV, remember we have a maximum limit for that multiplication. So we said, okay, let's find this BV. Since we have a limit, BV, those two, when they get multiplied, they are bounded. They have a maximum. So if we multiply these two terms together, we'll get to pi over 12 Fn divided by L. That's what we are going to get. Now, but the truth is, I'm just going to bring this example from 307. I don't know how much you are going to like it, but do you remember when we said to you, if you have a shear force F acting on this surface, then by saying that tau is equals to F over A, where A is this area. A is this area. What you are doing actually, you are saying that you will get a stress which can be represented by a depth rectangle like this, and everywhere on the surface you have a value tau which is the same, 50. Everything is 50, 50, 50, 50 everywhere. But we told you, be careful, be careful. This is the average. You take the force, you divided it by the area. In reality, the accurate distribution is this. When you have that force F acting on that gray area, the distribution is like this. It's actually some zero in here. Here, it is not zero. And it has a maximum value which can reach, let's say, maybe 80 megapascal, while this one is always 50. Correct? This is the same. When you push that, you actually generate a distributed pressure. And turns out, if you go and do your experiment, you will end up with that pen over here. This is our friend having or being subjected to a pressure distribution like this, with this point having P max. Now, if you look at this mathematically, you would say, whoa, I mean, the only way I can describe this, we're going around a circle, is to have some sort of integral going from 0 to pi, and then find a way to get this equation to know how the pressure is changing. So this has already been done. I'm not going to do it here, so you go read it in the book. But it turns out that P maximum is this. This P maximum is similar to tau maximum, which is, I really forgot. Is it 3 over 4 V over A or 4 over 3 V over A? Something like that. So that maximum value has, look, if F divided by DL, the average multiplied by 4 over pi. So this is greater than 1. So it's going to amplify the average by a little bit. Okay? And we will end up with a weir factor, a weir measure W, which is equal to F1, F2, K, F, F1 and F2, the two constant, and then K, the weir factor, F is the force, N is the speed, T is the time, divided by 3L. This is gonna give you how much is the wear. Now, you can imagine that as the material wears out, clearances will change and everything will change. So you can imagine that we will have some sort of a criteria. If I know the wear factor, I can predict how much do I need to reach the critical amount of wear. How much is that, right? And so this is what we are going to do next. But with some recommendation trade-off, as explained in the book, it is recommended that L, the the length divided by the diameter ratio supposed to be greater than, less than or equal to 2, and greater than or equals to zero point 0.5. This ratio will turn out to be helpful for design analysis and so on. So we're going to talk about it in the next class. Okay, Shabam, that's it for today.